So this is a good lecture to make sure you're sitting by someone you like to talk to. Because whenever locks get involved, there could be some heads started exploding a little bit and thinking about all through the cases. So we're going to work through some of those examples a little bit. But to get started, let's just make sure we're all on the same page with a few terms. And those terms are deadlock, livelock, and starvation. Okay, so I just want to go through those because these are all issues that can occur when you have synchronization problems in your program. So I want to make sure I give some examples of these so we're clear on the terminology, and then we'll use that terminology later in the lecture. So deadlock, and it's a term that I've heard people, those of you in the audience have said earlier in class. So it might be intuitive what it might mean. Here's an example that I drew up. This is an intersection, and I've got 4 cars on the intersection. And my claim is that none of the cars can make progress. So do you agree with the claim? And so if cars are not allowed to back up, what does every car need in order to make progress? It kind of needs the road in front of it to be clear, right? So this yellow car needs the road in front of it to be clear, but that part of the road is not clear because it is held or it's occupied by the green car. So why doesn't the yellow car just wait for the green car to get out of the way? Well, the green car can't make progress because it depends on a resource, a part of the road that's held by the next yellow car, and so on and so on. So notice what the conditions are here for this form of deadlock. Everybody needs to have a resource that they can't get, and you can't. And then the idea is that you don't relinquish that resource until you get everything that you need to make progress. So in this case, the yellow car is kind of holding on to or occupying this territory, but it needs this territory, and it's not going to let go of this until it finishes its job. And then finally, the problem is that we have a circular set of dependencies. I can't go because I'm waiting on you. You can't go because you're waiting on someone else. They can't go because they're waiting on me. And so you need all of these conditions to hold in order for there to be deadlock. So for example, here's a photo that I took of a deadlock situation in real life. Which is very similar to the cartoon that I put. Here's a bus, and the bus made a little bit wider turn than it should have. Or you could argue that this car probably ignored a little something on the road that says, please don't pass this line because buses need to turn here. And all of a sudden the bus can't make progress because that car is there. The car can't make progress because the bus is there. And why is it the case actually that we get deadlock? We need the ability, we need to be in a situation where we can't relinquish resources. So relinquishing the resource here would be what? Would be backing up, right? And you can't see it from my photo, but neither of these folks can back up because everybody's kind of filled in behind them. And so ultimately, it certainly isn't actual deadlock, because otherwise if it was real deadlock, the road would still look like this. So eventually people start backing up, but you have effective deadlock. Here are a few more examples of deadlock for our more nature-loving folks. And so make sure you can convince yourself why these are deadlock. Nobody is willing to relinquish a resource because they don't trust the other party. And since that's the case, no progress is being made. Okay. Now, of course, the reason why I'm telling you all this is this can obviously happen in computing systems. Like a simple example might be, imagine we had thread A and thread B. And thread A pulls data out of some work queue and puts results in some output work queue. And thread B is supposed to pull data out of this work queue and put the data back in the one on the top. So you might be in the case, well, thread A says, well, I'm not going to pull any new work because I have nowhere to put my output. So thread A doesn't drain its input, and it's waiting on B, but B can't make any progress because there's nowhere for B to put its output. That's an example. And the example of deadlock that we hit earlier in class is when we were talking about message passing. Remember I said, there's this subtle bug in our original message passing code where we said everybody was going to send and wait for their message to be received, and then they would turn around and receive, right? And so that was an example of deadlock as well. Everybody was blocked on essentially the same call. And as I alluded to earlier, you need these 4 conditions for deadlock to actually occur. We need to have resources that can only be held by one party at a time. That's the mutual exclusion. Like only one car can exist in this part of the road, or only one thread has data in its input queue. Like this input queue is exclusively for this thread. You have to have a situation where you can't back up. So once you kind of start this process and you acquire, like the part of the road that you're in, we're assuming that you can't back up or relinquish those resources to free things for other people. The only way you can free up resources is to keep going and complete things, complete jobs. Last is, 2 and 3 are kind of similar in that there's no preemption. Like if you actually could take the thread off the processor and relinquish the resources, that's kind of basically relinquishing resources. And then the most important one is this 4th one, which is the circular set of dependencies. I'm waiting on you while you're waiting on me. And since, because if there wasn't a circular set of dependencies, what would happen here? How would this resolve itself? Imagine that there were only 3 cars in the intersection, not 4. If there were only 3 cars, someone would make progress, right? And as soon as they finish their task getting through the intersection, they would relinquish resources for someone else. And then someone else can go, and so on and so on. Okay, so that's a deadlock. In deadlock, nobody is making progress. Like, nobody's doing anything, no progress is getting made. That's a little bit different than the situation of Livelock. So in Livelock, that's a situation where you're constantly doing things, but no real progress is being made. So for example, imagine that we had these cars in this intersection, and they did have the ability to back up. And so every car saw that they had sort of reached this sort of impasse where nobody can make progress, and imagine everybody backs up. And then everybody's like, oh, the intersection is free, I'm going to go. And they back up, and so on and so on. So this is a situation of Livelock. So it's called Livelock because everybody's making progress. Like there's not, you see operations happening left and right. If you had like system logs, you'd be like, yeah, stuff's happening. But then you'd be like, but nothing real is happening. So this is another problem that we can get into. What's the most common day-to-day example of Livelock that you run into? What's that? I thought I heard a murmur. What happens all the time when like you kind of walk up to a door and somebody else is like, you go, oh, you go, you go. That was like the most common social Livelock that definitely happens. Or where you're walking and both of you walk to the same direction and then you both walk the other direction to let somebody go by. Those are all examples of real life Livelock. Okay, so we have Livelock, and yeah, so Livelock is a state where we are actually doing stuff, but nothing is all that interesting. Okay. And then last, there's the condition of starvation. And so here's another road example. Imagine that there was a yield sign here. So the yellow cars on the horizontal road had a yield sign and had to yield to traffic on the main vertical road. So if this is a busy time of the day and the green cars are just a steady stream of green cars, they're going to make progress. We're going to get a lot of stuff done. But certain operations, such as yellow cars going, are going to get completely starved out. Because if they have to yield to the green cars and the green cars never have a hole in the traffic, you're just going to be sitting there all the time. Right? For those of you that are go over to the beach very often, it's like trying to get on 101, or sorry, get on Highway 1 on a weekend when you're just like stuck in Half Moon Bay and you're trying to turn on to Highway 1 and you can just never get on the road. So it may look like you are, like if you're debugging this thing, to you, it might look like, oh, shoot, maybe I have deadlock because I'm not seeing any yellow cars do anything. But we are completing useful transactions. We are letting the green cars go. Okay, so those are just 3 things to keep in mind throughout the lecture. Deadlock, Livelock, starvation, all things that we can kind of mess up. All right, so before I start talking about locks, I think this would be a good time to review this diagram that Kunle put out in front of you last Thursday, I think. Yeah, last Thursday. Yeah, so that was the first time we talked about cache coherence. And so before we get into thinking about how locks are implemented, I want to make sure, because you've only seen this once technically, and this is like the first, you're doing homeworks on this now, that people have a little bit of an idea about what's going on here. So first of all, if you had to describe the purpose of cache coherence, why did we talk about that last week at all? What's the problem that cache coherence solves? Yes, sir.
We don't need to go all the way back to memory to deal with.
Oh, okay. Well, yeah, okay, so it solves the problem of we want caches.
Yes.
Yes. And if you have multiple caches, they are copies of data. And whenever you have copies of data and you have writes, you've got a real problem of you got to keep those copies up to date. That's the problem that cache coherence largely solves. Good. And I guess if you had to, maybe building on that, if we had to say, what is the general strategy that these cache coherence protocols that Kunle talked about, if you had to give like a high level, like what are they all, what's the main idea of them? Or what are some of the key principles? Like what does this diagram even mean?
Yeah. It was like the multiple revisions, single writer.
Okay, so one version of this is saying, if you make copies of something and you write to it, you have a problem keeping those copies sort of in sync. Don't allow there to be copies if you're writing to something, right? So then the first name of the game is the minute you write to something, all other copies are going to have to disappear so that there's not a problem where you cannot access data that might be stale, okay? And how did that get ensured? In other words, like what does this diagram actually do?
Well, so I guess it's like when you go to the bus react, all the other ones go invalid, like they basically go.
Okay, and so good, and so I'll repeat that in a second for people remote. But the first idea that I want you to think about is that this cache coherency diagram it's a policy, it's a rules of the game that all the caches have to be agreeing to. So this is the state machine, this is the logic that every cache executes individually on their own to ensure that coherence is met. And one of the biggest parts of coherence is to make sure that when one person is writing to the data, nobody else is, so nobody else has data. So the way I want you to think about this is, and Kunle gave you one of these examples before, is I want you to think about a sequence of memory operations performed by different processors or different caches. And then I want you to think about what would I do if I'm cache 0 in this situation? And what would I do if I'm cache 1 in this situation? Right? So just to start, let's just say that the first cache loads a variable or loads an address. Okay? And what that cache does is, talk to me about it. Like, what does that cache do? What does this text on the slide actually mean? There's like issue bus read load line x and s state observe bus read. What does that mean? We have two caches, and let's just say I'm cache 0, and I want to read from this address. So what do I have to do?
Yeah, I was just going to say, so what cache 0 is doing is it's broadcasting the fact that it is reading like this particular memory address to all of the other caches, so that if the other caches also have that line inside them, then they can kind of like follow the protocol and transition accordingly.
So
Cache.
Good. So just keep in mind, the name of the game is that all of these caches are working together. And whenever the state of my cache changes, I have to tell all the other caches about it. Because they're making decisions based on knowledge of what I'm doing. So in this case, if I load address X, I have to shout out to all the other caches and say, hey, by the way, I'm about to have a copy of this. Which basically is saying, if you ever get around to writing to it, you gotta let me know, right? So that's me as cache 0 shouting out, I'm loading line X, and now what allows me to load it into the S state?
Still consistent with
It's still consistent with memory, yes. Yeah, so basically, first of all, I'm loading it essentially with a permissions to say, I promise I'm only going to read from it, right? And that means that other caches know what? If I'm only going to read from it,
they can also read from it.
They can also read from it. Exactly. So that's what. Okay. So that's what I did. And notice that cache 1 did nothing at that point. Why is that?
Nothing to change in our state.
Yeah, like I yelled out, "Hey, I've got the line containing X," and the other cache is sitting over here saying, "It's not in my cache. I could care less." Right? Exactly. Okay. And so then I loaded to it again. I read the value again. And what happens? Absolutely nothing. Why does absolutely nothing happen?
Because we don't allow anything to us to.
Yeah, why do I not have to tell anybody about this?
The hit. Sorry.
It's a hit. My cache state did not change. They already know what my cache state is. Exactly, right? So now let's say I want to write to the thing. Okay, what do I have to do?
Issue a re-exclusive.
I have to yell out that I'm about to write to it. Okay, and what does everybody else have to do?
Validate it.
Yeah, and now in this case, the other folks don't care because they don't have it, right? So in this case, doesn't do anything. And now if I want to write to it again, same thing. If I write to, so now the other processor wants to write to it. What is the other processor going to do? So it's going to shout out, "Hey, I need to write." And what do? So first of all, I can't keep my copy. And in this case, since I have written to the value, I better put the most recent value back out of memory, right? So I'm going to put the data back out of memory so the other processor gets the latest value. And then I got to drop. Because why don't I just keep it in a shared state? Because it's going to be stale, right? Because the other person's going to write to it. Exactly. So now if another load by the other party doesn't matter to me because I don't have the value. If I want to bring it back and read it, I'm going to say, "Hey, I want to read this value now." The other processor is going to flush it out to memory, and then what are they going to do about their cache? They could keep it in shared because they're like, "Well, I can't write to it anymore because there are copies around, but I'll keep it around because if I want to read from it, I don't want to actually take that cache miss." Okay? And so I'll let this, we won't go into the rest of this, but these are the things that you definitely need to be able to walk through and step through in your head. You did one last week. I think there's one on the homework assignment and stuff like that. Okay, so with that in mind, now let's think about implementing a lock. And I'm going to give you, because you're used to using a bunch of locks, but we haven't actually talked about the underlying details very much. So what I'm going to do is I'm going to give you an instruction that's not a load or a store, but actually a little bit of both. It's a load compare store. So imagine that you have a machine instruction, and just to keep it simple, I'm going to call it test and set. But in practice, these types of machine instructions are very different. They might be compare exchange or load link store conditional. But imagine you have this instruction called test and set, which takes the value or reads a value from memory at a designated address. And if the memory's address is 0, it sets it to 1. That's all it does. It loads it and sets it to 1. Okay. Now let's think about how I might use this to implement a lock. So here's my simple assembly code for implementing a lock. Here's unlock. Let's start with unlock, actually. So imagine you had a variable that was 1 if someone had the lock, and 0 otherwise. If you're the thread that has the lock, how might you unlock the lock? Just write 0. Makes sense? Okay. And here, what is the lock procedure? The lock procedure is try and execute one of these test and sets, which says if, and it's storing the value of loaded from memory here into this register. Okay, so I'm going to read the value from memory, and if it's 0, I'm going to set it to 1, all in one step. This is one instruction, one atomic instruction. And if the value I read from memory is 0, what can I conclude? I have the lock. If the value that I read from memory is 1, what can I conclude? I don't have the lock, and I actually am going to branch, if non-zero, back up and try again. So it's basically I'm saying, while the value in memory is not as 1, keep trying this test and set thing. If you ever see it to be 0, by the time you're checking to see, oh, was I the person that set it to 1? If you're the person that set it to 1, you have the lock. And then the minute you unlock, presumably some other thread can come in and now succeed with one of their test and sets. Okay. Now, like for example, if you were running on an Intel chip, you wouldn't have test and set. You might have something like compare exchange, which is a little bit more elaborate form of things. And offline, I think it'd be kind of fun to study this, to say basically, hey, can you confirm that essentially this is a lock with compare exchange, which basically is using some x86 flags registers and things like that. It's doing basically the same thing. Okay. Now here's why I spent some time talking about or reminding you about coherence. Imagine that we have three processors or 3 threads, and they're all trying to get this lock. Okay, so remember what they're doing is they're saying, while test and set fails, keep trying. And as soon as test and set succeeds, I know I have the lock, so I can do my critical section kind of thing. Okay, so let's think about what happens. So processor 0, let's just say that processor 0 is the processor that first tries to get the lock. That test and set, I'd like you to think about as a write. At least from the coherence protocol perspective, it's a write because it's modifying the variable. Okay. So since it's a write, processor 0, or processor 1 in this case, is going to try and execute its test and set. That test and set is going to cause an invalidation. Right, because that's a write operation. Even if it fails, it's a write, because it's an atomic operation that may write. Okay. So at this point, if that test and set succeeds, I think you would agree with me that processor 1 is holding the lock. Okay. So let's think about what happens at the same time. So processor 2, at some point in the future, tries to obtain the lock. And what is processor 2 going to do to try and get the lock? It's going to execute that test and set instruction. What's going to happen to the cache line? Processor 1 and 3 will have to invalidate, and the cache line containing the lock variable is going to move over to processor 2. Okay, so keep in mind what just happened. A lock is just a variable that has a value. That variable is just in the address space. It's cached. And so even though processor 1 has the lock, processor 2 has a valid cache line containing the variable that the lock is. So having the lock and having the cache line are 2 different things. So there's nothing stopping from processor 3 from coming in and trying to get the lock at this point, right? So that cache line is actually just going to bounce over there to processor 3. And then all these tests and sets by processor 2 and 3 are failing, right? Because they can't get the lock, which means the cache line is just doing this. Does that make sense? Now, what happens when processor 1 wants to unlock the lock? It's got to issue a bus read X. It's got to invalidate everybody else. It gets the line in exclusive mode. It does the write to set it to 0, and then one of those tests and sets on one of the other processors, let's just say processor 2, succeeds, and now processor 2 has the lock. So think about what's going on here is I'm a core, I have a lock, I'm in my critical section trying to do this thing so I can release the lock. And first of all, there's all this bus traffic flurrying around between all the other processors as they spin. And second of all, actually I have to take a cache miss to get out of the lock, which kind of stinks too, right? Because that's time that other folks are not doing what they need to do. Yes?
Why does the test and set unload it, but line even if it doesn't actually modify it at all?
Well, the test and set is an atomic instruction. So there's a couple ways I can answer that question. One is the instruction may or may not update the line, but you need to have write access if it's going to go through, right? So like there's no way you could implement it as a atomic, or I guess if you implemented it as a let me give a bus transaction to read the value, and then another bus transaction to sort of upgrade or get write permission, you're issuing two bus transactions. So by definition, it's not atomic, right? Mm-hmm. And on x86, there's actually a lock prefix on a number of instructions, and that lock prefix basically kind of does that. It says, sure, under the hood, this will be implemented as multiple transactions, but they've got like a lock flag on them, meaning that we're not going to allow any transactions in between to the same thing or something like that. So you can just effectively think about it as atomic, independent of what the implementation is going to be. Okay. So I already alluded to this, but I want you to be absolutely clear here that on the previous slide, what is the duration of time that the thread running on P1 had the lock? It was the entire slide. What was the duration of time where P1's cache contained a valid copy of the line containing the lock variable? It was only for a second at the time of lock and for a split second at the time of unlock. It's kind of interesting, right? And so like a simple lock like this has some properties that if we added more and more threads, more and more processors that are trying to actually grab this line, it might take an increasing amount of time for the core with the lock to actually be able to grab it in the right state again. And you actually see that in this graph, where this graph is just kind of like the cost per lock unlock, which is actually going up as a function of the number of processors in the system. Because basically, like in order for me to get the cache line in the writable state, I'm contending with increasingly large number of processors. It might take me longer to get that exclusive access, and might take me longer to literally unlock the lock. And so every unlock period actually starts getting big and gets higher. Okay. So now you might say, oh, wow, it sounds like we could do a whole lecture on how to efficiently implement locks, which we're not going to do, but you could think about some of the properties you'd like to have in your locks. Like you'd like it to be fast, like low latency, like when you call lock, you don't have to wait for very long, or you call unlock, you don't wait very long. You'd like your lock implementations to not basically DOS your system by generating a bunch of interconnect traffic while everybody's waiting, everybody's spinning. You might like it to scale to large numbers of cores. You actually might like it to be fair. There was nothing about that previous implementation here that guaranteed that all the processors would ever get the lock, right? Like maybe processor 1 and processor 2 just keep getting it, and there's nothing to ensure that processor 3 actually would in this implementation. So implementing locks efficiently can actually become a pretty interesting thing. So let me just give you a few small refinements. So here's a different lock that has the same test and set instruction. So now I'm writing in C code to make it a little bit clearer. Test and set does the same thing. If it returns the value in memory, and if the value in memory is 0, it atomically sets it to 1. So this sort of this if test and set is 0. Well, that means I executed a test and set and the return value is 0. So I now know the value in memory is what? 1. And I also know that I have the lock because it was 0 when I started the test and set. I know it's 1 when I ended it. And I know that I executed the test and set when nobody else had the lock, which means I have the lock. Okay. So that's what this is. If test and set returns 0, return, which means I have the lock. But what's this thing doing? Why do I have like while here? This is correct. Like there's not a bug in this code. This is correct code. But can you kind of back engineer what I'm trying to accomplish? Yeah.
test instead will try to get the right access to the line.
Right. So this called a test and set is a read exclusive, or a request to write to the value. What is this while the value of lock is 0 doing? It's just saying, oh, just keep checking to see if it's 0, because if it's not 0, why should I even bother doing a test and set? So what's the implication of this? So what happens here is, while the lock is taken by someone else, I am going to spin on reading to see if it's still locked. If it ever becomes unlocked, I'm going to try and jump in there and do my test and set. If I fail, I'm going to go back to waiting until it's unlocked again. Why might this be a better idea? Yeah, finish this up.
Each of those cache lines.
So I'm turning a bunch of writes into a read, or into a bunch of reads. So let's go back to my diagram. Let's think about what happens. Same thing as before. P1 grabs the lock. P1 does a write, a test and set, to get the lock. All other processors are spinning on, is the value still 0? If I'm reading over and over and over again, all the other processors are just holding that line in what state? S state, yeah, the shared state, which means they're just taking a bunch of cache hits. So for the duration of the critical section, they're spinning, they're doing work, but that work is not creating global traffic out to everybody else. Processor 1 still has to take a cache miss to get the line back in the what state? To release the lock, processor 1 definitely has to take a cache miss. It's a cache miss to get exclusive access again. That's where the write to set the value to 0 occurs. And then everybody else all of a sudden invalidates their line, because they had to. Their next read back into the shared state finds that the value is 0. And then they all jump in and try and actually do a write. So you're going to get a flurry of, if you have P processors, you're going to get P minus 1 writes. Or if you count this one, it's O of P writes on every lock release. But during the critical section, you get no writes. So this is kind of nice, right? Like, it also helps in that while I'm in the critical section, I would love to have an uncontended bus, because maybe I'm doing reads and writes to other variables and I don't want to wait on an interconnect. So everything calms down during the critical section. At the end, there's this feeding frenzy where everybody says, oh, I think I can get it. And that's actually where you take P different write invalidations. So we're pretty good. We like what we did here, right? Like we got rid of this like continuous flurry of traffic whenever we're in the critical section. I'm still doing it with one integer. My lock variable is just one integer. I haven't tried at all to make things fair. There's no guarantee that anybody's going to win. And I slowed things down just a little bit, because now when the lock gets released, you have to do two things. You have to do a read and then a write, or a read and then a test and set, and not just a test and set. But I'm not too worried about that extra instruction of latency, to be honest. Just to give you one more design, here's a different thing that echoes how it might work if you're going to go get a sandwich or you go into the deli counter. Like, how does that work in real life, right? Like, you show up at the counter, and how do you know when your turn is? You take a ticket, right? And so the butcher or whoever's the deli person or the sandwich maker is like, okay, when they finish a job, they increment the current pointer. Okay, and so that's what's going to happen here. So now I have a lock that's not a single variable, but actually two integers. Let's ignore wraparound for now, just to keep it simple. And I have an integer for now serving, which is where the thread that has the lock is the thread that has the ticket matching now serving. And then we have next ticket, which is when a thread wants the lock, it walks up to the counter and says, can you give me a ticket, a unique ticket ID? Okay. So let's look at lock. It's my ticket, my local ticket is going to be an atomic increment of next ticket. It's just like, give me the next available ticket. And then I spin while my ticket is not now serving. And that is largely a bunch of reads. And now releasing the lock, when the lock is released, the thread with the lock just increments now serving, so it has to get exclusive access to now serving and does a write, does an update. But now look what happens. If you have a lot of waiting threads, it's not like everybody tries to get the lock now. Only one thread is going to try and write. And actually it doesn't even need to write at all. It just needs to do a comparison. So now a lock release is actually only one write, this write. And the thread that acquires the lock actually doesn't have to do a write at all. It only has to do a write when it sort of enters the waiting queue. So it's just another example of ways you can actually reduce contention. And in this one, actually, this is fair. Because you get in line, and the first person in line you're going to be served in FIFO order. Okay? So it's pretty cool. I don't need an atomic operation to acquire the lock. I need an atomic operation to start waiting, but I don't need an atomic operation at the point where I get the lock. So it's pretty cool. There's only one write per lock release. Okay? Now, what it did do is it required your hardware to provide something a little bit more sophisticated than test and set. The hardware had to provide an atomic integer operation, atomic add in this case. So now you're asking a little bit more of your hardware here. So here's a list of a bunch of atomic operations that you might find on any platform these days. Here are atomic operations that I took from the CUDA built-in library, CUDA standard library. So if you're running anything on NVIDIA GPUs, you have all of these atomic operations at your disposal. Okay, so like a atomic increment, which is just what we had, is it takes the value pointed to here at this address and increments it by this value. So that's a read, modify, write. It's like read the value from memory, update its contents, write it, all in hardware guarantees that that's atomic with respect to all CUDA threads. And I'd like to call special attention to this atomic compare and swap. So CAS is atomic, is compare and swap. So this is the logic of atomic compare and swap. Now keep in mind that even though I'm writing it here as C code, this is an instruction. This is what the instruction does. So it's not like there are locks inside of this or something like that. So the hardware is providing some mechanism where this can be. And what it does is it takes a pointer to an address. It takes a comparison value and a new value. And it says if the value in the address is the same as the comparison value. So the value out of memory, if it's equal to compare, please write this new value in. Otherwise, leave it unchanged. Okay? And I wrote it here in this syntax to kind of give you a sense that like basically a write is essentially happening regardless of whether or not it's unchanged though. So I'm setting the value and address to either its previous value or this new updated value. Okay? So given this, what if I asked you to implement something like atomic min? This is something that's a common question that I might ask on a homework assignment. I don't think I did this year actually, but this is a good one to study. So atomic compare and swap just says, grab a value from memory. If it equals this value called compare, please update the value in memory to val, else do nothing. What if I said, I don't want this, I want something much more useful, like I want you to read a value from memory, I want you to compute the min of this value and some other value, and I want you to write the new min back out to memory. Yeah.
You just do like old is greater?
Old is greater. Close. Close. What do I want to know in any atomic operation? What I want to know is that no other thread has set the min lower than what I... So let's just say that the current value of min in memory is 100. And I'm coming in with 90. So if there was nothing else on the system, my answer should update the minimum to 90, right? But what if after I read 100 from memory, but before I wrote 90 back out, some other thread had the value 80 and updated memory to have 80. And I come in and write 90, I've messed things up. right? So I know that my operation can succeed if I can guarantee that no one else has come in while I was trying to do this min operation. And how do I know if nobody else has come in?
Use a lock.
I can, but we're not going to use any locks here. I don't really care if nobody else has sort of come in. I only care if the min has changed. That's actually the only thing that matters to me, right? So if I read the value from memory, compare it with my min, and then go, oh, if my min's lower, I'm going to write it. I'm going to write my value, but I only want that to happen if the value in memory is the same as what it was when I got this whole thing started. It hasn't changed, right? That's exactly what compare and swap is going to do for me. So let's take a look at this. Atomic min is I read the current value out in memory. I'm going to call that old. Then I look to see, okay, is my value, in this case x, is it smaller than old? I'm going to put that here. And then I'm going to say, okay, I want to update the value in memory if nobody else has changed anything. So I'm going to do an atomic compare and swap on the memory address, and I want to make sure that the address in memory is still old, and if it is, please update it with new. Okay? And compare and swap always returns old, and so that's how you know if you succeeded. So compare and swap always returns the value in memory. So if the value in memory equals old, I know now that the value, I've updated it to new. If the value in memory is not old, try again. Yeah.
In some sense, it feels like this question of has a different processor like already written to this address is also being kept track of via the cache states, right? Like if the cache state was invalid, then perhaps a different one might have it in a modified state. Do we just not have?
It's a great question. Okay, so let me answer it in two ways. First of all, the game that we are playing right now is the only primitive you have access to is compare and swap. So in that game, you don't know anything about the state of the cache. But what you're saying is that if I had the cache line, and for some reason I lost it, then some other operation has intervened. Now, to be honest, in the cache coherence protocol, that operation could have been a read, which would not have modified this at all. But let's just say I knew it was a write. Like let's say I invalidated my line instead of dropping it to the shared state or something like that. If you had some way to get access to that, then you could provide me some alternative solutions, right? And there is, in your practice problems, the non-required practice problems, there's an instruction, a pair of instructions called load, link, store, conditional. And that's kind of what those instructions do. Load link says load a value from memory and at an address. Store conditional says store a value to that address provided that it hasn't been touched by any other processor since the last load linked. Those two implementations can ride the coherence protocol really easily. And in fact, there's a practice problem that I think I gave you which says imagine you have MSI coherence, how would you implement load link store conditional? So load, link, store, conditional, I believe even to this day, are kind of the preferred primitives on ARM.
Yeah.
Uh-huh.
On most risk objects.
Yeah, I mean, I'm not sure if because they didn't have cache coherence before, so now they probably leverage the cache coherence protocol to implement them, but before they probably just had some processor state or something, right, where they probably...
Caches and risks.
Yeah. Cool. Yeah, because I remember reading the instruction manual just like a couple of years ago. It was like you can have up to this many outstanding load, link, store conditionals or something like that. So on like some tiny processors, there's probably still some table or something that's like, yeah, okay. Yep, exactly. So what you're proposing is a very common operation on ARM. And so it's exposed to you via load, link, store conditional. Here's another great exercise, and I'm actually going to leave this one to you, which is given atomic cache, build a lock. And remember, how do we build a lock? We build a lock to say if the value in memory is 0, make it 1. And so it should be a pretty obvious thing to do. Yeah?
On the last slide, if we had an order like, it would be 100, and then 90 and 80 updates have been like rechecked. What if it was like 100 then 80 and then 90? I mean, that seems like
Yeah, so imagine I have the value 90 and you have the value 80. Okay, and the current min is 100. Okay, so let's say I read 100 from memory, and I'm going, oh, 90 is less than 100. I should probably write 90. Before I get around to writing 90, you come in. You say 80 is less than 100, and you beat me to it. You write 80. Now imagine if you look at, that's weird. Now imagine that I go ahead and write my 90. We're incorrect. Like the code is broken now. So I need to know, like I've read a value, I've done some comparisons or whatever, and then when I do my write, I have to say I only want this write to occur if the value is still 100. Because my value, the value 90 that I'm writing in there is the correct answer provided that it started at 100. But if you've come in and changed that value, in this case, my atomic cast is going to fail because the value in memory is not old. It's not 100. So when atomic cast returns to me, it returns to me 80. I go, whoa, 80 is not equal to 100. Therefore, my atomic cast must have failed. I need to try again. So I go load the value from memory again. I now observe 80. I compute a new min, and I go, oh, my 90 is bigger than your 80, so it should just stay 80. And then I try again. Mm-hmm.
Yep. Then it would go through and then it would see the update.
Yep.
Okay.
Uh-huh. Yep.
Isn't this inefficient? So let's say you had the value 90 and the current value was 80. Why in the world should you even go and try to write it to update it?
Well, I could make my program better, which says if the new min is not the same as the other one, just bail. Yes. Uh-huh. Yeah. Yeah, I could definitely make my program more efficient. And that would be similar in spirit to like this test and set lock, right? Yeah, exactly. Mm-hmm. Yeah, you could do that. Right? So the point here is if you have an atomic cast, you should be able to easily implement everything on this slide. Right? And moreover, you should be able to implement lock and unlock too, right? Because lock and unlock are just like atomic, if it's 0, set it to 1, right? And so, the implementation of lock looks just like this, right? And if you want to be a little bit more clever, the implementation of the test and set lock from before looks a little bit like that. Right. So on an exam or on future homeworks, I will assume that you're familiar with compare and swap. Now we'll always give you the definition, but it's very common exercise to say, given compare and swap, can you create an atomic primitive of some customized nature given that? Okay. And we already talked actually about load link store conditional as another pair of atomic instructions. So some systems give you atomic casts. Most systems actually give you load link store conditional, and everything gets built up from that. Right. So just a few other things, like for example, in some of your assignments, you've used atomic in C++. You might be wondering a little bit about what that means. Is just keep in mind that if you wrap, at least in modern C++, if you wrap a variable in atomic, the operations on that variable are assured to be atomic. So one way to do that would be, let's say if we had I++ automatically increment I, the implementation of atomic increment could be lock I ++ unlock I, be valid. But you can believe that most implementations say for certain operations on certain variable types, if there was an efficient hardware solution, it would in fact use it. So if there was an atomic increment in the system, I++ on an atomic type event would actually translate into an atomic increment instruction. For more expensive stuff, it might actually be implemented under the hood as a lock. And actually any variable of type atomic, you can actually query, is it lock free? And it'll tell you a little bit about how it's implementing that atomic operation. So it's kind of fun. The other thing that it does, and that we're not talking in too much about, is when you use these atomic variables, or like locks, you have to be really careful about relaxed consistency. Like if you were implementing these things. Imagine you had this lock implementation from right here. and your code called unlock, which is just write 0 to this address. And let's say that there was an operation up above this, which would have been in the critical section, right? Imagine if, due to relaxed ordering, those operations got reordered. So another processor saw the unlock and then saw the write to a value in the critical section. That would be very bad. Your lock would essentially be useless. So I'm writing these implementations assuming we have a sequentially consistent memory system. A real implementation of lock on a relaxed memory system would actually have a memory fence here to make sure that everything that came after that lock or before that lock, for example, was not reordered with respect to other processors. So I do want to point that out. Like, you will encounter relaxed memory consistency if you are in a job like a driver or OS ladder where your job is to implement synchronization primitives. If you are just using synchronization primitives, you always assume that those primitives have properly inserted the memory fences to give you the strict ordering that you actually expect. Okay, and I think that's about all I'm going to say, really on this. So one of the reasons why you use atomic int is not just to have atomic operations, but to make sure the compiler implements those fences around there so you do not get unexpected relaxed memory consistency issues. Okay? All right. So that was just like a half a lecture just on, it's kind of interesting. Kind of interesting to see what happens when you call lock or unlock, and there's a lot of complexity there. And if you get it wrong, like the speed of these locks can be very, very different. Any questions? And the cache coherence and memory consistency are front and center, actually, in the different implementations, for sure. Yeah?
I guess we saw 3 different ways to implement the lock. Like, which one is most common?
Well, there's also a bunch of other ways to implement the lock that I didn't talk about that they almost certainly tell you in an operating system class. So all of my locks are what you would consider to be spin locks. The processor is still just spinning. There's also the idea of actually sleep the thread. Like literally sleep the thread, pull it off the execution context. My understanding, if you look at most lock implementations, there's a difference between mutexes and spin locks sometimes in these libraries. So a spin lock will do something like this. Most sort of heavyweight locks will actually probably spin a few times to try and get the lock. And if you can't get it after a few spins, then it does the heavier weight systems calls to pull you off the processor. I know pthreads was implemented that way. It doesn't, like, if you try and get the lock, the first time if you fail to get the lock, it's not like they sleep you immediately. They're like, okay, maybe it'll be available in a split second. So try a few times, and if you fail a couple times, then we'll take you off. Okay, so let's talk actually about using these things, which is equally complex, but a completely different topic. So now I want you to assume that you have locks, okay? And here's a linked list. So take a look at this and just confirm to yourself, maybe even, and there's going to be a lot of code coming up, that this is in fact your run-of-the-mill job interview linked list, which has insert and delete. I'm not even handling the edge cases of inserting the front of the list just to keep the slide simple. We have a node which has a value and a next pointer, and this is insertion and deletion into a sorted linked list. So your operation on insert would be create the new node and then walk forward into the list until you find the first node that is bigger than me, and I need to insert myself right before. Yeah, so the current list item is current, and if the current value is greater than the value that I'm trying to insert, then we quit and we move. We keep walking forward and then we break, and then if so, the new node's next is the current. The previous node's next is me. So in other words, I'm walking forward until I find a value in the list that's bigger than me. Previous points at me. My next points at the node I just found. Okay. So what I want you to think about a little bit now, and this is maybe, like everybody's sitting around staring at me, this is where I'd like you to talk to yourself a little bit. I'd like you to tell me what could go wrong if I run this in a multi-threaded setting. There are no locks on the code right now. So think about what could happen if you're deleting two nodes at the same time. Think about what could happen if you insert two nodes at the same time. Just think about all the possibilities of what could happen here. So I'll give everybody about 90 seconds or so to do that. Like, is there a way you could lose nodes? Is there a way you could lose the rest of the list? Things like that. Go for it. And yeah, feel free to talk about it with your neighbors, of course. Yeah. All right. Should we talk about it a little bit? I see some people still puzzling over things, which actually is pretty. If you're not still puzzling over things, I'm impressed. Because even with something as simple as a linked list, this can get kind of hard. So let's maybe look through some visual examples that might help everybody here. So let's consider double insertion for now. So let's say that I have this list, 3, 5, 10, 11, 18. And let's say that I want to attempt to insert 6 and 7. So I want to kind of insert right next to each other in the list. So what's going to happen, like what's the right answer for thread 1? Well, thread 1 is going to walk forward, find this point in the list where the 6 should go. And if there were no other threads involved, that previous should point to 6 and 6 should point to current. No problem at all. Right? We get something that looks a little bit like this. Patch it right in. Okay? Now, let's think about what thread 2 would do. Like thread 2 would basically want to do the same thing. 5 should point to 7. 7 should point to 10. Okay. Now, what's going to happen when both of those are going on at the same time?
I think you might get like a double loop, like single loop.
Well, let's say thread 1 just says, okay, 5 is going to point to 6, and 6 is going to point to 10. And then if thread 2 comes in later, 5 is going to point to 7, and 7 is going to point to what? 10. And what just happened? We just lost an insert. And if it goes in the other order, that could happen too. So it kind of depends on which one we want to say wins, but assuming thread 1 updates previous next before thread 2, then thread 2 is going to end up winning. So I just lost an insert. Let's think about another case. How about one insert and one delete? So let's say thread 2 is trying to delete 10. So thread 2 is like, oh, okay, I want to get rid of 10. So 5 needs to point to 11. But that's kind of interesting because 5, according to thread 1, is pointing to 6, which is pointing to 10, which is deleted, and might no longer have a valid next pointer at all. And now all of a sudden I've lost the rest of my list. So, and then we could do some similar things with simultaneous deletes. Simultaneous deletes, you might get a double delete. You might actually delete memory that's already been deleted. So if I go back to this code, and I said, in the spirit of do the simplest possible thing to make this correct, what would you do? Yeah, in the back.
On like both of insert or
Can you tell me where you put the locks?
I mean, I started put it near the beginning and at the end.
Okay, so what you're going to do is you're going to put one at the beginning of insert and one at the end of insert. And then, is that it? One more at the beginning of delete and the end of delete. Why is everybody laughing? It's good? It works. It works? Are you sure? Are you sure it works? Look closer. Even the simplest coarse grain locking is busted. Well, yeah. We're assuming it's the same lock. Yeah, that works. Look closer. I claim deadlock. Now, of course, if you used one of these unique locks in C++ that automatically unlocked when it went out of scope, you'd be fine. But this is just like a little example of even something as simple as throw your locks globally around everything with multiple exit points from a function can kind of get you. Okay. So if I had to let me jump forward, like if I had to be careful, it would look a little bit like this, right? Exactly, yeah, the same spirit of your solution. Okay. So what's good and what's bad about this? What's good is clearly that it's correct now. What's bad? I mean, the entire access to the data structure is serialized at this point. And that's going to be trouble. Why even spawn these threads in the first place, right? Good. Okay, so that's not, may limit parallel application performance, and well, if most of your performance was in the data structure, it's going to definitely limit your action. You may not care if most of your I don't know what's going on today. Okay, so what I'd like you to think about, you don't need to see the slides for this, I'll bring it back up in a second as soon as I, is how would you do better? So talk that over for a second. So clearly different parts of this data structure can be edited at different times. Okay, so just for the sake of making sure we get through everything, I mean, I am not surprised people are still puzzling over this. I should probably give you at least 5 minutes to try and figure something like this out. By the way, on an exam one year, I decided to do this for a rotating binary search tree, and it was hard. But I promise I won't. What's the gist of some of the stuff that you're coming up with? So first of all, I think it should be clear that I should be able to do some insertion or deletion here while another thread is working on another part of the list. The data structure should definitely afford that. What are you thinking about and how you might accomplish this? Yeah.
I think probably a lock on a per node basis. So then you can just add a lock to a node struct.
Oh, okay, so let's throw a lock in every node now. So there's no total list lock anymore. There's a lock per node. That's a reasonable start. And now the question is what's the order that you would take those locks to make sure that things were okay? Let me give you a starting example. One example would be I'm going to take a lock on 3, and then I'm going to release the lock on 3 and put a lock on 5. And then I'm going to release the lock on 5 and put a lock on 10. That's one example. Another one would be I'm going to lock 3, and then I'm going to lock 5, and then I'm going to lock 10, holding all of these locks. And then I'm going to do my thing, and then I'm going to release the locks. So, how did anybody start discussing a policy for how you might maintain as much concurrency as you possibly could, but also still got to be correct? So what's what about my simple example? Let's take a lock on 3, let's release it, and then let's lock 5, and then let's release it, and then let's lock 10. Yeah.
Something might change in between my opportunities and all.
Okay, so if I lock 3. If I release the lock on 3 and I don't have any locks, that's the moment where I know nothing about the data structure anymore, right? That means that by the time I go to 5, it might be gone, right? So there can't be a situation where we have no locks. Otherwise, that's definitely going to be trouble.
If you want the lock at 3, it means that only you can update it. So it's you are responsible for that link.
So if I'm holding the lock on 3, what do I know? Nobody else has the lock on 3, so that's true. How can we use that information to have guarantees? So if we lock 3 and then we lock 5 and 3, well, we certainly know that nobody has got locks on 3 or 5. Okay, and then we also know that nobody has locks on 5 and 10. That's helpful.
Yeah. Maybe you only need to lock the nodes before and after, the one that you attach to make that part.
So there should be some notion of I only need to keep the locks on the blast radius in some sense, right? I only need to keep the locks on things that if someone else modified, it would cause me a problem, right? And so the real question is how many locks is that here? So one way, in this diagram, this gentleman on American Ninja Warrior, he's on the overhead bars, right? And so this idea that if we ever lock and then unlock and then lock again, that is deadly. That's basically what happens if he's never holding on to at least one bar, right? Gravity takes over, right? It's not going to work, right? But he's doing this thing where he's making sure he's holding on to at least one bar at a time. And the question that we have now is like, how many locks do we really need? So here's a scheme where that embodies this hand-over-hand locking idea, where I'm inspired by what you're saying. I'm going to take the lock on 3, and then I'm going to take the lock on 5 before I release that lock on 3. Right? And then what do I do? Oh yeah, I'm deleting 11 here. So I need to keep going, right? So I need to take that lock on 10, release it, take that lock on 11. Okay. And at this point, these are my thread 0's previous pointer and current pointer in the linked list traversal. So should I release the lock on 10 and then delete 11? No. What's the motivation behind that? So if why can't I? I'm only deleting 11, so why do I care about 10? So I need to modify 10, right? And so since I'm going to be modifying 10, what am I worried about? That next pointer of 10, well, really what am I worried about some other thread doing? Another thread could delete 10? What if another thread inserts after 10? Yeah. So to delete, I want to make sure I always have a lock on current and previous. Okay? And so let's say if thread 1 comes in and wants to delete 10, why are we protected? Because if the rule to delete is I have to have a lock on the thing to delete and the previous one, I know that nobody is deleting the previous one. Why? Why can't thread 1 get in there? Because I have the lock. Okay, so why am I not worried about someone deleting 18? Why don't I need the one in front of me? So if I have the lock on 11, nobody can be deleting 18. Okay. So why am I not? Well, now let's think about insert. If I have the lock on 11, how do I know that nobody's inserting after 11? Because I'm going to have a lock on 11. How do I know that nobody's inserting after 18? I don't, but I don't care because it won't impact me, right? So this hand over hand, 1, 2, 1, 2, 1, 2, 1, 2, always keeping a lock on previous and current is actually going to work out here. Yes?
With the way insert was set up, if you had, thread 2 come in and start after thread 0 and thread 1 in this case, would it be blocked in if its operation was to insert after 18, but it started after these two operations, would it still have to wait?
That's correct. So that's a nice. So this is not necessarily maximum concurrency, right? Because I have a thread 2 coming in. Let's say this is way down the list, right? Or actually, let's say it's a really long list, and this is happening at the beginning. Thread 2, T2, which is not on the slide, is not going to be able to get past these and get ahead, even if it's going to operate way over here on the list. And why do we have to make sure that it cannot pass things up? Because while it's traversing, these T1 or T0 better not be deleting those nodes that it's traversing, or inserting actually in places, right? Because we can lose the list with inserts and stuff. So yes, a linked list is a very sequential data structure in some ways, and unlike some other data structures, you don't have as much concurrency in it. Now, if we had a guarantee that T1 and T2, T0 were not writing to this portion of the array, then we could think about it. We could think about a different lock type that was allowed multiple readers or something like that. But we have not discussed that here in this class today. Okay. All right. So here's the hand-over-hand locking solution for this this program. There's actually a few kind of tricky invariants in that, I actually had to take there's actually a lock on the list as well as a lock on the node. The point being is, remember our invariant is I need the lock on current and I need the lock on previous. If you're deleting the first node, you either need a dummy previous or you need an extra lock somewhere else. So this code is correct. There's actually ways to make it slightly more performant where you more aggressively unlock things, and I'll leave that to the class to sort out on the discussion board. Okay, so this is a good just different things that you might come up with, like incorrect. You actually could end up deadlocking. It's hard to deadlock a little bit in a linked list because it's kind of one directional, but and then there's like the cost. Like now imagine, like remember your cost of a linked list was like just chasing a pointer. Now you're taking a lock on every step. That's going to slow things down big time, right? So it may be the case that big coarse lock might actually be better, like limit concurrency, but get done quick. So who knows? You'd have to performance profile. If it turned out that taking a lock on every step to the list was too much, what are some ways that you might what's a middle ground between a lock on everything and a lock on every node? Yeah, you could like say I'm going to take a lock for every 5 or 10 nodes or something like that. Yep, exactly. So you can play. So on your own time, a very good exercise would be to let's just go with a standard binary tree and a binary search tree, and try and write the code yourself of insert and delete on a binary tree. No rotations or anything like that. Okay, so I want to hint at one more thing that is not going to be on your midterm, but we'll bring it back for the final a little bit, is how to make concurrent data structures that are thread safe but don't use locks. And you've already seen one example of it in class. Atomic min, I think you said just use locks, right? And I was like, well, no, you can't use locks. That compare and swap implementation is an example of a primitive that is safe but does not use locks, right? And the main idea was to say, I'm going to basically speculatively go forward with whatever operation I'm supposed to do, and at the last second, I'm going to check to see if something's changed. And if something's changed, I'm going to start all over again, right? And that's different from locks. Locks say, when I enter, nobody else can go. In this lock-free way of thinking, your idea is to say everybody goes, but everybody can check at the last second to see if things are safe. And if things are safe, they do their right. If they don't, they sort of abort and try again. That's the big idea of lock-free. Okay, so and one of the reasons why people are so lock-free is people talk about it, I think, a little bit more than necessary. But like all of your concurrent collections in Java are lock-free implementations, for example. And I want you to think about a case that in our class, most of the code you write is your application is the only thing running on the machine. You're using parallelism to run really fast. Imagine you're writing some big database or some web server, and there's hundreds of thousands of threads or something like that. Concurrent threading is being used to hide latency of network traffic or something like that, not necessarily parallelism. Imagine you take a lock as a thread, and then you get swapped out by the OS. You get context switched out. All of the runnable threads are sitting there spinning or trying to get a lock, and the thread that has the lock just got swapped out in its critical section. Those are the types of examples that really motivated lock-free data structures. Because just because you have the lock, if you are not doing anything, somebody else should be able to come in and do their thing, right? And so that's the difference between blocking and non-blocking. Everything that I've shown you in this lecture so far has been, except for the atomic cast stuff, has been blocking, meaning that if you can't get the lock, you just stop. And now everything I'm going to talk about is you just run forward and hope for the best, right? And that's what lock-free algorithms are called. So let me give you just one simple example before we... Here's a queue. This is very much like a queue that you would write at a Microsoft interview again. This is like a big... and so I'm implementing a queue as an array, and as you push, you increment head. As you pop, you increment... Or as you push, you increment tail. As you pop, you increment head. Okay? And imagine you're doing it with just 2 threads. The pusher thread is just incrementing the tail. The popper thread is just incrementing the head. So you don't have 2 threads ever accessing the same variables, and this code is thread safe with 2 threads. Okay? And I'll stop there. I don't want to hold you any later. But in the slides, what you'll find is I gave an example of how to do that with allocation, with like a queue that's implemented as a linked list. And I give you an example of a stack. So the idea of a lock-free stack is you try and pop. You do all this stuff to pop. And again, at the last second, you check to see has anybody else popped. And if nobody else has popped, which you can detect with compare and swap, you just go ahead. And the nice thing is that if you're in the middle of a pop and you get swapped out, then all the other threads come in and they just do their pops. And when you get swapped back in and you complete your operation, you will detect that the world has changed, and you just try again. So these lock-free data structures are designed for highly concurrent situations when there's a bunch of different threads and tasks on the same machine to try and get around some of the problems that can occur in a blocking situation where you have mutual exclusion. Okay? So I just wanted you to know a little bit about them. We're not going to talk about them too much more in the class until we get to the modern day version of all of this, which is transactional memory. Okay, I'll let you all go. Sorry for going a little bit over.